Hey PSTAT students, this is going to be the last video that I'm going to be posting for you. Your test is this Friday, and I know that seniors are officially done with classes and grades, but it's important that you take this test seriously. If at all possible, do your best. Try not to just blow it off. I know the circumstances this year are crazy, and I know that some of you have had to do other responsibilities since we've been off, like working and things like that. But I wanted to at least spend a few more minutes going through this one other handout that I posted. It's a final review, uh, and with this handout, there's several different terminology and concepts that could be on the AP test, kind of big ideas. Some of these are things that were actually eliminated from the 2020 test because of time. So I will mention that as I go through the handout. And there are some things on here. So I actually have a handwritten key that I'm going to put on Google Classroom for you as a reference as we talk through this. You can look at that also. So question number one, what is power and how do you increase it? So power is the probability of correctly rejecting a false null. So power is recognizing that the null hypothesis is false when it really is false. So another way you might think of that is the chance we're going to catch someone who's guilty. That's power. So question two, in what sorts of scenarios can you apply chi-squared? We didn't get to chi-squared this year, and it's not part of the AP test. Don't worry about that one. Question three, how do you figure out if you should apply a z-test or a t-test? This is important, kind of big concept, big idea, and so make sure you know this. So anytime I am going to deal with proportions, one proportion or two proportions, I'm going to use a z-test. Anytime I'm going to have means, either single mean, differences of means, things like that, we're going to use a z-test, t-test, sorry. So z-test is proportions, t-test is means. Okay. Jumps to question 6 on your handout for some strange reason. Don't worry about that. What does the p-value tell you? Well, the p-value is the probability of getting the results that we get assuming the null is true. So the probability of getting the sample that we got assuming that that null is true. Question 7 is, what is a type 1 error? So type 1 error is the when we actually have a true null but we reject it. So we reject a true null. That's type 1 error. Type 2 error is when we fail to reject a false null. That's a type 2 error. So if you recall, when we used the letters, the type 1 error is called alpha. The type 2 error is called beta. All right. And then if we think about power, back to the first question, power is 1 minus beta. And the significance level is alpha. All right. And then number 8, how do you compute confidence intervals in general? So in general, a confidence interval is always going to be, let me expand this a minute. So a confidence interval, erase my other math that I was just working on. In general, confidence interval, we always have a statistic plus or minus a critical value multiplied by the standard deviation of the statistic. And so when we think about a statistic, this could be x bar, this could be p hat, this might be something like x bar 1 minus x bar 2, etc. That's what we're talking about. critical value, Z star or T star, and then the standard deviation of this. And when we deal with proportions, remember, we're estimating that standard deviation, so we call it a standard error. Actually, we call it standard error with with means as well. So question number 9. How do you determine critical values on your calculator or your table? So on our calculator or table, we're going to use either inverse norm or inverse t. So suppose I want to do critical value. So suppose it's 90% confidence interval, and I want to use, suppose I'm figuring out what Z star is. So if I know that there is 90 in the middle, I know that there's 5% on both tails. So I would do inverse norm of 0.05, and that would tell me what that is. Now that's going to actually give me the negative version of the Z star. If I did inverse norm of 0.95, I'm going to get the positive version of that. If we do inverse t, we need to specify how many degrees of freedom that we're using. So don't forget about degrees of freedom when you do that. All right. Next up, the next question is, what's the central limit theorem? So let's go back to handout a second. So central limit theorem is so the central limit theorem says as n increases, an x bar distribution is going to become more and more normal, and the standard deviation of that x bar distribution is going to get closer and closer to the standard deviation of the original x distribution. The other thing that the central limit theorem says is that as long as we have large enough samples, and 30 is a typical bar, the distribution of all those sample means is going to become more and more normal. It's going to become bell-shaped and unimodal, no matter what the shape of the original distribution. Number 11, how is the shape of a regression line related? Okay, in that one we don't need to worry because we did not have time to get to regression. Actually, I take that back. We just okay. We touched on regression. There's going to be a little bit of regression. There's not going to be regression inference on the AP test this coming week, but we do need to know this one. So slope of a regression. Well, the rule is that the slope of the regression line, and we call this B1, is equal to R times the standard deviation of Y divided by the standard deviation of X. Let me write that up on the board a minute. So if I have y hat is equal to b sub 0 plus b sub 1 x, then this is called the y-intercept, and this is called the slope. And so the rule is that b1 is equal to r times s sub y over s sub x. And so remember, R stands for the strength of the linear relationship. Could be negative if it's a negative linear relationship. Could be positive if it's a positive linear relationship. And then we have the spread of the y's over the spread of the x's. All right. What point do all regression lines go through? And that point is x bar comma y bar. So x bar comma y bar is question 12. The mean of the x's and the mean of the y's. How do you interpret r squared? So we could think of r squared as the percent of variance from y bar that can be explained or accounted for by the linear relationship. If you don't remember that, I posted an assignment a while back, I think it might have been week 2, that there were some videos about r squared. You might want to revisit that if you don't remember what r squared represents. Question 14. 4 things that we always talk about when we want to describe a set of data. So SECS, sex, we want to make sure we talk about spread, extreme values, the center of the distribution, and the shape. So when we talk about shape, remember we're talking about things like unimodal, roughly symmetric, skewed right, skewed left, and we want to use qualifiers. Very rarely is something perfectly symmetric, so we could say things like roughly, approximately, things like that. How do transformations affect summary statistics? So if I take a set of data and I add some number to every set, so if I had like a set of data 1, 2, 3, 4, 5, and I add 10 to every number, and I think about how does that impact all these different statistics. So if I add 10 to every number, the mean is going to just be 10 more. The median is going to be 10 more. So you could say this is plus k, mode plus k. The spread of the distribution won't be the same because essentially I've taken that distribution and I've shifted it one way or the other. I've just picked it up. I haven't stretched it out. When I'm I'm just picking it up and moving it. So those measures of center will shift by just that, whatever you add. You can think of the same as subtracting as well. And then the spread won't change. The spread will stay the same. When we multiply by a number, so suppose I took a set of data and I doubled every number. So if I have a set of data like 1, 2, 3, 4, 5, and I multiply by 10. So then I have 10, 20, 30, 40, 50, and I think about how does that impact the results of all these different statistics? Well, everything is going to be multiplied by 10. So in general, everything is going to be multiplied by k along here. So everything's multiplied by k. All right, remember IQR is interquartile range, so make sure you remember that as well. Whenever we describe a scatter plot, we always talk about three things. We talk about the direction, the shape, and the strength of the relationship. We hadn't gotten into bivariate data when we left this year in March. It was the next unit, so we missed quite a bit of that, but that was week 1 and week 2, maybe even week 3 on the assignments that you did already. Number 17. For a residual plot, make sure to comment on all of these things. So make sure you talk about the balance of the positive and negative residuals. So in a residual plot, we should see kind of random scatter. We shouldn't see any kind of change in how that scatter is. Ideally, we don't have a lot of spread in our scatter, but it should be random. We shouldn't see where the scatter gets wider as you go across. We shouldn't see that. The size of the residuals should relative to the actual y values. So what that means is if we have, if our scale is in the millions, then the residuals are obviously going to be bigger. If I have numbers that aren't very spread out originally in the data set, and my scale is only counting by ones or tens or a decimal amount, your actual residuals are going to be much smaller relative to that data. So the third one there, want to make sure that the residuals are randomly distributed. I mentioned that, random scatter. What is an SRS? So we're going way back to the beginning of the year. SRS stands for simple random sample. SRS, simple random sample. And remember, whenever we do a simple random sample, we want to make sure we have 2 requirements met. Requirement number 1, that every member of the data set has equally likely chance of being selected. And requirement number 2 is every set of size n has an equally likely chance of being selected. So if my sample size is like 10, and I'm taking a random sample of groups of 10, I want to make sure that every group of 10 is equally likely. So for instance, if I'm taking a sample of kids in our class and I'm randomly choosing 5 kids, it wouldn't be a simple random sample if I broke the class in half and said I'm picking 3 from this group and 2 from this group, because even though I'm doing random samples within each of the groups, a group of 5, every group of 5 isn't equally likely. So make sure you remember those 2 requirements. Number 19, what's the difference between an experiment and an observational study? Well, with an experiment, we want to remember that you always have some sort of treatment and that's imposed on your subjects. So in general, observational study, we're just kind of sitting back and looking at some set of data and making conclusions on it. Experiment, we are imposing something. We're giving it some sort of treatment. The other big thing is with experiments, we can prove or show cause and effect much better than we can with observational studies. Retrospective versus prospective studies. So retrospective is in the past, something you're looking back on. Prospective studies, we're looking forward. All right. Number 21, these are important concepts when we design an experiment. We talked a lot about these at the beginning of the year. If I were you, I would revisit those chapters in your book this week at some point. I would study these concepts. Make sure you know some of the basics of experimental design, because very likely there's going to be some kind of question about experimental design in one of the 2 questions this year. So control. So this is allows the experimenter to rule out alternate explanations. So we're trying to eliminate confounding effects of extraneous variables. So remember earlier this year we did the caffeine experiment, and one of the ways that we maintain control is I gave you all the same amount of pop. The other way we controlled is we had the same time frame where we all were in the room doing the experiment. We could control the temperature of the room. We could control trying to eliminate these confounding variables that might produce differences in our results as much as we can. Randomization, well, randomization helps eliminate factors we don't see. So I can't control what you did before you came to class. Some of you might have had PE when you did that caffeine experiment, so you might have had a fast heart rate already from the class you just came from. Maybe some of you were really bored in the previous class, so you might have had a real slow heart rate. So I couldn't control that. So what we do is we randomly select groups to give different treatments to, and that randomization helps balance the differences between the groups. And the idea is that if I balance those differences, then I don't have to worry so much about factors I can't control. Replication. This just means I'm repeating the experiment over and over. And we can replicate by having more trials, and we can also replicate by doing multiple experiments. So there's 2 ways of replicating there. Blocking, and this is where we try to control factors we can see. And so blocking is very similar to stratifying. Stratifying, we're thinking about taking a sample. Stratifying is a method of sampling. Blocking is used when we group people in an experiment. So for instance, if I wondered if males responded differently than females to caffeine, I could block by gender, and then within each gender I could randomly assign half of people to the caffeine and half to the non-caffeine. So a block is like a group based on a certain characteristic you think that might matter in the experiment, might matter in that in the thing you're trying to measure. Confounding variables. So confounding variable, this is something that is statistically related to the independent variable, but so it could cause issues. We're not sure what's causing the effect. So an example on here with a credit card study, if we had a low rate, so we lower the rate on the credit card and then we get rid of the annual fee, versus another group where we had a higher fee and a higher annual rate. Well, if we're trying to tease out which of those is the thing that really matters, we wouldn't want to group them together, because then they're confounded. They're put, we don't know if it's the rate or the fee the annual fee that's causing the change in our variable. So those are confounded together. So you try to avoid that. Try to just hone in on one variable as much as possible. 23. How do you find the expected value of random variable x? So let me quick do a probability distribution on the board here. So if I have a probability distribution and I have some random variable x, and then I have the probability of x. So suppose it might take on these three values. Suppose it could be a 0, a 1, or a 2. So suppose this is 0.25, this is 0.3, and then this is 0.45. And if I wanted to figure out what is my expected value, so my mean expected value of x, I would simply do 0 times 0.25 plus 1 times 0.3 plus 2 times 0.45, and that will give me whatever I should expect from that on average. Okay, we could also do the standard deviation of x. Remember, your calculator actually can do this, so you could review how to do that on your own, but we could also do this by hand. So we would say, once we get our mean expected value, whatever that might be, we're going to take the probability of each event, so 0.25, and then we would do the mean, so whatever our mean is, mu sub x, minus each of those. So the first one was 0 plus 0.3 times, and then it would be the mean of this minus 1 squared plus. So this mean we'd fill in with what we got up here, and then we'd do the third one. So you should make sure you know how to do the mean and the standard deviation of a probability distribution. All right. Next up, what does it mean for two events to be independent using probability rules? This is really important as well. So if two variables are independent, or two events are independent, so what that means is that the probability of A given B has to equal probability of A. So in other words, the knowledge that B occurred does not change the likelihood that A is going to happen. So you could say it either way. You could also say if A and B are independent, the probability of B given A is the same as probability of B. So whenever we want to prove independence, we want to make sure that we show that conditional probability is not equal, or if it's independent, they have to be equal. Probability of A given B has to equal probability of A, and probability of B given A has to equal probability of B. Let me write that out just to make sure we all have it. I think I put it on the key that I will post. But so the probability of A given B is just equal to the probability of A. That's what independence means. And you could write it this way: probability of B given A is equal to probability of B. All right. The next one on there. One second. So what does it mean for two events to be disjoint or mutually exclusive? So these are the same thing, disjoint and mutually exclusive. It just means that probability of the events happening together is 0. They can't happen together. So P of A and B, remember, and is the upside down U. So probability of A and B is equal to 0. They mean the same thing, disjoint and independent. All right, binomial situations. So binomial situations, these are situations where I have two unique outcomes. A classic one is when I'm tossing a coin, flipping a coin, or when I'm rolling a die or a pair of die. Maybe a single die, and I want to say, I want to think about, I'm rolling it 10 times. What's the chance I'm going to get a 6 2 times? Or what's the chance I'm going to get a 6 4 times? And we write that out. So Let's just talk through a quick example. So let's go with that where I'm rolling a die. So if I think about rolling a die, and I want to know my event is getting a 6, and I'm going to roll it 10 times. Okay, and so the probability of success here would be 1 out of 6 every time. And every time the events are independent, that's a real important requirement of binomials. They're independent. So remember, Q is the probability of 1 minus P. So this is going to be 5/6 chance of not getting a 6. So if I said, well, in this situation, X is our random variable, and X is the number of 6s. That I'm going to get. Okay, so I want to know, what is the probability that X is equal to, I don't know, 3? What's the chance I'm going to get 3 6s? So I would say 10, choose 3. So 10, choose 3. And then I would say 1/6 to the 3rd and 5/6 to the 7. So this is a combination. This is the number of ways I can pick 3 things out of 10. 1/6 to the 3rd, 5/6 to the 7th. Notice that the 3 and the 7 add up to 10 because I have 10 events total. So that's important. Remember, on your calculator, you would say binomial. So this one is PDF because it's a single event. So PDF, and then you would do 10 is the number of trials, and then 1/6, and I want to know 3. And they will give you the headings in your calculator. Actually, you are going to need to make sure you have either the TI calculator on your Chromebook for your AP test, or that you know how to use Desmos to do this, because Desmos can do this as well. And so if you have questions, send me an email. I'll be glad to help you. So then let's do another one, same situation. What's the probability that X is, I don't know, let's say less than or equal to 4? So if I want to do less than or equal to 4, this, I'm going to do the same kind of thing. I'm going to start 10, choose 0, because I could have 0. That's an option when you do binomial. 1/6 to the 0, 5/6 to the 10, plus 10, choose 1, 1/6 to the 1, 5/6 to the 9, plus dot 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 plus. So reminder, on the AP test, you need to write all this out. This calculator notation is not preferred. You need to write this math notation. I don't know if you're necessarily going to penalize if you write this, but you shouldn't write just this. You definitely want to make sure you include some of this math notation. So we're going to write the first 2, and then we're going to write the last one. So 10, choose. So we're going to, in this one, 4. So I can just skip a few, and then I would do 1/6 to the 4 and 5/6 to the 6. And that would be in my calculator. I would, this is a CDF, so binomial CDF, and then I would do 10, comma, and it's 1/6, and then remember with CDF and binomial, it starts at 0 and it adds up to whatever number you specify. So if I want to go less than or equal to 4, I would include 4. So I'd go up to 4. The other thing to keep in mind, if I had like an in-between, so suppose I wanted to say, what's the probability of getting between, say, what's the probability that we're between 2 and 5? So to get that, we could write out the long math notation. I'm going to jump right to the calculator just to focus on that. So I would do binomial CDF. So we're adding up to 5. So we'd say 10, comma 1/6, comma 5. Then we take away the binomial CDF, and then we would go 10 comma 1/6, but we would end, so we wouldn't want to cut off 2 because we want to include 2, so we would go up to 1 when we do that. So that's a little detail, but we haven't talked about that in such a long time. I want to make sure I remind you of that. All right. Hypothesis testing. Make sure you check your assumptions and your conditions. You should have this out. If you have your textbook still, there's assumptions and conditions in your textbook. You could use that as a reference. Otherwise, there's some nice things on the internet with assumptions and conditions. If I think of it, I'll try to look for a good website that lists the ones that you need as a reference. That's something. It's open notes on the 2020 test, so you shouldn't have any issues with that. More likely, they will ask you why you need to do these certain assumptions and conditions. Really, what's the significance of them? So you might want to revisit that in your textbook. The practice test question that I did last week with you, I posted a video on Friday. That could help you as well. All right, question 28, describing distributions. If a distribution is skewed to the right, then we would say that the mean is going to be larger than the mean. The mean is going to be larger than the median. So remember, skewed right means it's you got a tail to the right. The mean isn't resistant to that skew, so that mean is going to follow the skew. So in this one, the mean is going to be larger than the median. If a distribution is skewed left, the mean is going to be less than the median because that mean is going to be stretched to the left side because it's going to follow it. You do need to be careful. Just because the mean is less than the median or the median is less than the mean, we can't necessarily conclude the shape of the distribution. You don't know necessarily that there's the strong skew. It could be a bimodal distribution, something like that. So just a little caution there. Okay, some things about experimental design. So with experimental design, when it asks you what sort of experimental design you have, the common answers are either a completely randomized, block, or matched pairs. So there was an activity I posted in the assignment where you had to read an experiment and try to decide what sort of design it was. But just wanted to revisit this. So completely randomized means you are taking a sample and then you're randomly assigning treatments to the entire population. So suppose you have a population of 100 subjects and you have 3 treatments, you're going to just randomly assign each of the 100 people to a different treatment. And that would be completely randomized. Block is when we group the subjects or experimental units in some kind of similar way. I mentioned gender. Could be maybe you're trying to figure out if ethnicity, it has some impact on something. Maybe you could group by ethnicity or by gender or by weight or by height, things like that. Whatever you might think might impact the response to those treatments. And then the last one there is matched pairs. This is similar to block, except our blocks are size 2. So we just are comparing 2 treatments when we do matched pairs. And so, for instance, suppose I want to know if a certain tire on a bike is more effective than another tire or wears quicker than another tire. So I might randomly take, so every bike might have both tires on it, randomly, some in front, some in back. And then so that would help us control for, everyone rides a bike differently. But then I have the same person riding with both tires on that bike. And I could try to see if one of the tires wears differently than the other tire. That would be matched pairs. Any of these things that you hear me talking about, you're not sure of, take note of, Google them. You've got the power of the internet. You've got your hopefully you've got your textbook. I actually put a link on Classroom. You can go back and read the textbook that way also. But also, if you're feeling real uneasy about a concept, or just even a little uneasy, or you just want to talk about something, send me an email and I'd be glad to talk. Your test is on Friday. I am available again Thursday. Haven't seen many people at the Google Meet lately, but if you're available, I'm there every week on Thursday. And I can even do another session if there's any interest. Have a great week. Hope everyone's doing well. I miss you all. Take care.